3I/Atlas just made its closest pass by Earth. And what we learned this week is the kind of thing that makes astronomers sit up straight, stare at the numbers, and quietly say, wait, that can't be right. Because for months, we've been hearing one story about how big this interstellar visitor is. Then on December 23rd, scientists dropped brand new calculations that basically flipped that story on its head. And the reason they can do this is wild. They're not measuring the size with a ruler. They're measuring it with a whisper of motion, an almost invisible push, so small it's like trying to detect a single extra heartbeat in the entire planet. Here's the setup. When a comet warms up, it doesn't just glow, it vents. Ice turns to gas, gas jets out, and that jetting creates a tiny rocket effect, what scientists call non-gravitational acceleration. It's not gravity pulling it, it's the object pushing itself. For 3I/Atlas, that non-gravitational acceleration was measured at about 89.3 times 10 to the -9th astronomical units per day squared. Translate that into human terms. It means that every day, 3I/Atlas ends up moving about 13 kilometers per day faster than the day before. That sounds dramatic, but compared to Earth's gravity, it's microscopic. Only about 1/5 millionth of what you feel standing on the ground. Basically nothing. Except it's not nothing when you have precision tracking from hundreds of observatories. When your position data is razor sharp, even a tiny push becomes a fingerprint. So how do you turn that fingerprint into a size? The strength of the push depends on two things: how much gas is escaping per second, and how fast that gas is moving when it leaves the surface. And here's where it gets spicy, because the James Webb Space Telescope measured both. The gas is escaping at roughly 1,600 kilometers per hour, and the total mass loss rate is about 150 kilograms per second. So scientists ask the key question: what size object would make those two measurements, outgassing plus acceleration, actually match up? And the math points to a diameter around 1 kilometer, more specifically, somewhere between 800 and 1,000 meters, assuming typical comet-like properties. Now let's talk density, because comets are weird. They're not solid rock like an asteroid. Most are more like a dirty snowbank full of voids, porous, fluffy, full of empty space between chunks of ice and dust. A typical comet density is around 500 kilograms per cubic meter, about half the density of water. Using that assumption, you can estimate the mass, and the result comes out to roughly 260 billion kilograms. A 1 kilometer wide object weighing about 260 billion kilograms. So far, clean story. We measure the push, we measure the gas, we infer the size. But here's where reality starts glitching. Earlier this year, between May and September, scientists tracked 3I/Atlas before it got close to the sun. They used data from over 230 observatories worldwide, with position tracking accurate to around 0.028 arcseconds. To visualize that, it's like being able to pick out a coin from more than 100 kilometers away. And across that entire 5-month span, they could not detect any non-gravitational acceleration at all. You might think, okay, maybe it was too subtle. Nope. Their detection limit was about 300 times more sensitive than the more recent measurement. If the object was getting pushed the way the December paper suggests, the earlier data should have screamed it. So what does that imply? If the acceleration truly stayed below that early detection threshold, then the object had to be way more massive than 260 billion kilograms. Because if you have the same outgassing force, but you don't see the motion, the only way to hide it is with a lot more mass. Harvard scientist Avi Loeb previously calculated that if the acceleration was below the detection limit, then 3I/Atlas must weigh at least 33 trillion kilograms. That's 33 billion tons. And at normal comet density, that points to a diameter of at least 5 kilometers, which is basically the size we'd been hearing for months. So now we've got a contradiction that is not small. December calculation, approximately 1 kilometer wide, approximately 260 billion kilograms. May-September constraint, at least approximately 5 kilometers wide, at least approximately 33 trillion kilograms. That's a 5 times size difference and about a 120 times mass difference. Same object, same universe. Two answers that don't want to be friends. So what's going on? Let's run through the best explanations, plus a couple extra that get even creepier. First, the acceleration number itself has been revised. NASA and other teams have been refining their models since the earliest measurements. Non-gravitational acceleration values can change as you improve the orbit fit, add more data, and better account for uncertainties. If the true acceleration ends up being lower than the early estimate, the inferred diameter would rise, potentially moving that 1 kilometer upward. Second, mass loss over time. This one is simple and brutal. In May through September, the object was far from the sun, colder, quieter, heavier. As it approached perihelion, especially by October, it got cooked by solar energy and could have shed enormous amounts of material. If it was much more massive earlier, the low acceleration back then makes sense, and the higher acceleration later would show up as it gets lighter. Third, asymmetric outgassing plus rotation. This is a huge one, and it's the kind of thing that can absolutely fool you. If gas is blasting from one or two hyperactive regions, the rocket thrust depends entirely on where those jets are pointing. And if during May-September, the strongest jets were pointing sideways relative to the direction that affects the orbit fit, perpendicular to the main track, you might not see a clean acceleration along the path. Then later, as the comet rotates and the lighting geometry changes, those jets could start pointing in a way that produces a measurable push along its trajectory. Comets do this all the time. It's like trying to judge a spinning sprinkler by watching one droplet. Fourth, the model assumptions. That density of 500 kilograms per cubic meter? That's a typical value, not a guaranteed one, especially not for an object that formed around a completely different star. If 3I/Atlas is denser than expected, the same acceleration would imply a smaller size or different mass. If the outgassing is more lopsided than assumed, the effective thrust changes. Tiny assumption changes can move the inferred diameter upward or downward a lot. And now two additional possibilities that scientists are actively mindful of with strange objects. Fifth, thermal lag and buried volatiles. What if 3I/Atlas wasn't really on, yet in early observations? Some comets don't vent strongly until heat penetrates deeper layers. You can get a delayed ignition where early in the inbound journey it looks almost inert. Then later it suddenly activates when buried ices, like CO or CO2, start venting through cracks. That would give you a low acceleration early, then a big measurable one later, even without needing extreme mass loss. Sixth, fragmentation or a rubble swarm effect. Here's a nightmare scenario for clean measurements. What if the object is not a single nucleus behaving nicely? If it's shedding chunks, or it's a contact binary, or there's a faint cloud of debris that changes the brightness and gas profile over time, your assumptions about a single solid body can break. Your outgassing measurement might be dominated by a fresh fragment, while the orbit fit reflects the bulk mass differently. The system could be evolving under our feet while we're trying to measure it like it's stable. So where does that leave us? Right now, the best honest answer is, this is what real science looks like when the target is unprecedented. Data comes in, models get updated, parameters get revised, and slowly the story snaps into focus. But what makes 3I/Atlas especially hard is the part people keep forgetting. This is an interstellar object. We have never studied a comet from another star system this closely before. That means some of our go-to assumptions, based on comets born around the sun, might be slightly off. The chemistry could be different. The structure could be different. The thermal history could be alien in the most literal sense, formed in another environment, aged under different radiation, maybe processed by deep time in ways our local comets never experience. And here's the genuinely unsettling piece. The unknown unknown that keeps this interesting. If our best instruments can measure a tiny rocket push, and our best math can turn that into a size, and those answers still collide head-on, then either the object is behaving in a way our models don't capture yet, or we're looking at a physical structure that doesn't behave like the comets we grew up studying. And that opens the door to questions we still can't fully answer. Is the nucleus solid or a porous foam? Are the jets steady or chaotic bursts? Is it one object or a system of pieces? Is it venting from sunlight or from internal pockets that wake up late? And if this visitor formed around another star, what does that say about how common or how weird these bodies might be out in the galaxy? So I want to hear your theory. How do you explain the 1 kilometer versus 5 kilometer contradiction? Which explanation feels most likely to you, and which one feels the most mysterious? Drop your thoughts in the comments, and if you want more deep dive updates on 3I/Atlas and other space anomalies, subscribe to the channel so you don't miss the next video. Merry Christmas, and I'll see you in the next one.